Okay, so let's define the derivative of a function. So we said what a smooth function was from a manifold into another. So now let's talk about what the derivative is. So let M and N be smooth manifolds. And F be a smooth map. Then its derivative at P is a linear map, so which we'll call, I'm going to call it dF with a capital F to make a distinction with the differential, which is only defined for real valued functions. So dFP from TPM into TF of P. Before I continue, let me just ask, is everybody hearing me well, even with the mask? Okay, the microphone is working, good. All right, so it's defined like this. And so it's a map that goes from the tangent space to M to the tangent space to N at the point F of P. Okay, so if my function, so if this is M, this is N, have my point P, here's F, and here's F of P. So the derivative will take the tangent space at P to the tangent space at F of P, and it's a linear map. How is it defined? Well, again, using derivations, it's very canonical. But so let me write the definition using derivations, and then maybe in a chart, so you can really see what's going on. So we have to say what happens when you apply it to a vector at the tangent space of P. So what is dF P of V? Well, this is supposed to be a derivation on N at F of P. So this is supposed to eat a function on G. So we take a vector here, and we take a smooth function on N with real values. So we have to see what happens when we apply it to N. And it's kind of very canonical. It's kind of the only thing you could imagine doing, which is basically just apply V to the composition of G and F. Okay, so, and you can check, so I guess the first exercise, so exercise, dF P of V is a derivation on C infinity of N at F of P. So that's just basically a consequence of the chain rule. Okay. But if you do it in charts, then you can kind of recognize the more standard derivative. So if you just apply this to, if you want to do it in charts, basically just look at the standard, the canonical basis here, ddxi, and see what happens, what derivation you get. So I guess this is the first exercise. And the second exercise is to look in charts. So yeah, so we can let phi x1 through xn be a chart, around P, and let psi, which is y1 through ym, they don't have to have the same dimension, be a chart around f of P. So now, if you can write this down in terms of the coordinates. So the observation or the exercise is that as a matrix, the matrix of dF from the canonical basis, I guess I can write it like this. So from the basis ddxi till ddyi f of P is equal to the derivative of f composed with phi inverse composed with psi I ddxj. No, I think it's the other. Well, it doesn't matter. You just have to see ij. It's either that or the transpose. Okay, I think to be fair, I guess we can write it explicitly like this. This applied to ddxi is equal to the sum of d psi composed with f composed with phi inverse I, j ddxi from j1 to m of d dyj. Okay, so maybe it's ji. Anyway, so it's exactly what you think. So you just have to look at this map in charts, and the derivative is that linearization of the map in charts. Okay, but it's very beautiful if you just write, very canonical if you write with derivations. Okay, so that's the derivative. In particular, if you have maps from Rn to Rm, everything is exactly what you think. Okay, so now I can define what an immersion, a submersion, and an embedding are. So definition, let f from m to n be a smooth map then f is said to be, so it's an immersion if the derivative is injective for all p in M. And it's a submersion if the derivative is surjective. For all p. And it's an embedding if f is an immersion and there is a continuous inverse. Inverse going from f of m onto m. And here when I say this, I really mean that f of m has the topology that's induced from n. So this is the same as saying that f is a homeomorphism onto its image. Okay? And just a few, the notation that's often used is for this one, usually we write like this. M immersive, there's an immersion from M into N. So usually we write an arrow like this. And this just means that it could self-intersect. And then a submersion, we often write like this, the arrow with two things. And an embedding, we usually write like this. And I think you've all seen this before, but I guess it's good to think of an embedding, an immersion that's injective, and it's still not embedding. I mean, an embedding is clearly injective because it has to be a bijection. But being an injective immersion is not enough to be an embedding. So I guess let me just write a remark. Well, before the remark, let's do examples. I think that's more enlightening. I mean, I can just do examples by pictures. So, if you draw a curve like that in R2, that's, of course, an embedding. Or you can find a parametrization that's an embedding of this. You can think of it as a circle embedded into R2. But if you do this, then this is an immersion. An example of a submersion, for example, is a projection. A projection is a submersion. But for example, if you look at the tangent bundle, the map from the tangent bundle down to the manifold itself, that's a submersion. That's an example of a submersion. And I think it's also interesting. So now, an interesting example of a injective immersion that's not an embedding is if you take an open interval, so you can take a map from an open interval into R2, that does the following thing. It goes like this. So the image, is this thing. This is not an embedding. So this is an injective immersion, which is not an embedding. And the reason is simple. Is basically, you can't find a map, a continuous map that takes this image onto the interval. Because, this image, when you look at it with the topology of R2, it's really like this. So the local topology around this point is like this. So if it was possible to do a continuous map like this, then, as you approached this point here, the image would have to approach the image of this point. But if you try to do an inverse, you're going to basically take, this point over here, and then this segment, you'll take over here. So you can't do it continuously. Okay? So that's an interesting example. And the remark, which is not a very hard fact, so I guess it could be an exercise, is that if M is compact, then an injective immersion from M to N is an embedding. So the problem here is that the domain is not compact. Okay? All right, any questions about this? Okay, so let me write this as another remark. Well, let me write it as a proposition. But I'm not really going to prove this. It's kind of almost obvious. But if you have an embedding, then f of m naturally inherits the structure of a manifold. So if you have an embedding, and when you look at the image of the embedding, that, if you can just take all the structure on M and push it into the structure on F of M. So this guy will naturally be a manifold that's sitting inside of N. Okay, and that's what we're going to call a submanifold. So that's one way to define a submanifold. So I guess you can say a submanifold is the following thing. So let M be a manifold. A subset Q in M is called a submanifold if the inclusion map is an embedding. Okay? By the inverse function theorem, that's the same thing as saying that for any point on Q, you can find a chart such that the a subspace of Rn gets taken to Q. But basically, that's what it is. Okay, so if you have your Q, I guess you can't see here. Let me draw here. So if this is your Q, and it's sitting inside an M, by the inverse function theorem, this is the same thing as saying that you can find a chart on M so that what's in Q is really just a disk in some R Q, where Q is the dimension of Q, sitting inside Rn, which is maybe another definition that you might have seen before. But it's the same, this definition is equivalent to say that a submanifold is a subset such that the inclusion is an embedding. Okay? Any questions? No. All right. So a remark is if Q is a submanifold, we can naturally see the tangent space at Q as a subset of the tangent space to M for every point in Q. Okay, so if you don't know this, it's an exercise, but it's a pretty simple exercise. Okay, and you can do it either with derivations, if you like, or with curves. And clearly a curve contained in Q is also a curve contained in M. You just have to look at the equivalence relation. Okay? All right. Questions? No. Okay. So definition. I kind of gave that definition in the introduction, sort of, but let me do it more generally. So if I have a smooth function from M to N, we say that a point y in N is a regular value of F if for every point in the preimage of y, the derivative is surjective. Okay, that's a pretty standard definition. And now comes an important theorem. the theorem says the following thing. If y is a regular value of f, then the preimage of y is a submanifold. Okay? So it's true. I mean, in the introduction, I said that when n is equal to r, but this is always true. And let's prove this. Why not? Oh, and let me just say something about the dimension. So if it's non-empty, so if this is different from the empty set, then we can compute the dimension. Then the way to remember is the codimensions are the same. The codimension is equal to 0. So actually, I'm only taking the preimage of a point. So then the dimension of this is equal to the dimension of m minus the dimension of n. Okay, so in the case that I had stated before, n was R, which has dimension 1. So that's why I said it's an n minus 1 dimensional manifold. But in general, it has that dimension. Okay. And later in the course, we're going to see what happens when you take the preimage of a submanifold. But just to kind of to practice our muscles, we'll do here just the preimage of a point. But actually, the proof is almost the same, as you'll see next week. But let's just prove this for now. And in particular, you have a bunch of examples of manifolds. Just take any smooth function from Rn to R, and you're going to have, or from Rn to Rm, and consider regular values, and you're going to have a bunch of manifolds. As long as you have a regular value. Okay, so the proof, as I said before, is just basically applying the implicit function theorem. But let's do that. I'm not doing everything of a manifolds class in one day, but why not do a few things? So let's pick a point in the preimage of y. And let's take charts around x and y. So take charts around x and y. So I'm going to just call the charts phi, as usual, from m to. And now I'm going to say that m is the dimension of m, and n is the dimension of n. So my m has dimension m, and my n has dimension n. Let's not get confused. So this is a chart around x, and this is a chart around y. Okay, and I know I can now write my function f tilde, which is psi composed with f composed with phi inverse, wherever it's defined. So maybe in a slightly smaller set. But I'm going to just keep calling it u. But I might have to shrink u a little bit. So from u in Rm onto Rn. And because I know that df is surjective, that's equivalent to saying that derivative of this guy, and I'm going to, as usual, suppose that p goes to 0. That's equivalent to saying that the derivative of this guy in, the Rn derivative is surjective at 0 is surjective. Okay? So now I can actually apply the Well, I guess now it's basically just the implicit function theorem. So by the implicit function theorem, we can find a diffeomorphism of U. There exists a diffeomorphism of U, or maybe a smaller neighborhood than U, but I'm going to keep calling that U. There exists a diffeomorphism, let's call it phi, from U inside Rm until U tilde, which is inside Rm as well, so that everything that goes to a fixed point, and let me just assume also that f of p here goes to 0. So that now when I compose with this phi, or when I maybe I'll do it like this. So that now everything that goes to 0 here is exactly what's on a m minus n dimensional plane. So such that f tilde composed with phi of x equals 0 if and only if x belongs to some r m minus n contained in Rn. So in other words, you can like split the Rm contained in Rm. So you can split your Rm into Rm minus n times Rn. And in this new, when you apply this diffeomorphism, basically the map is just going to be the projection onto Rn. So that's what the implicit function theorem says. That you can twist the base, the domain of the map locally, so that the map is just the projection onto Rn. So if you're 0, then you have to start here. Maybe you can write direct sum. Okay, so you have to start here. Okay, so that now is saying that this guy, now if you restrict it to this guy now is giving you a chart of the pre-image of y. Okay, so now when you look at, say, the inverse, now when you look at phi inverse, this goes from U into Rm, and you restrict that to the preimage of y. So this intersection with the preimage of y, it goes from it goes from this, which is a subset of m, into your Rn minus m minus n inside of Rm. So this is a chart. Now this is a chart for the preimage of y. So that's one way to see it. So I'm kind of constructing the chart explicitly, or if you want, this is enough to say that the inclusion is an embedding. Because under this map, the inclusion of this into M is an injective immersion that has the same topology. So you can think of the other map as being the continuous inverse. Okay, so it's slightly disorganized, but do you understand? Yeah. So if you want, you could let's see if we can just prove explicitly that this is an embedding. So what we need to do is we need to show. So if this is my inclusion of this into M, what you would like is it's clearly injective immersion. You just have to see that it has the same topology. I guess it's straightforward from here. So I guess this is enough. Like, we just need to prove that F inverse of y is a manifold. And this is what we need. So we have a chart for the inverse. Okay. Any questions about this? No. So like I said, this is just the implicit function theorem in action. Okay. So now I want to talk about something that's very cool, very important in manifolds, and you probably have seen it before, which is partitions of unity. So partitions of unity. So I have to talk about coverings before. Yeah, so I'm going to go back to topological spaces for a second. So definition. Let X be a topological space. So we say that an open covering So an open covering, I guess I won't define this. It's just a collection of open sets whose union is the whole set. So this is said to be locally finite if for every point, the point doesn't belong in all of them except for a finite number of them. So it doesn't belong to U alpha except for a finite number of alpha in E, in I. Okay, so in other words, I guess I can write like this. The number of alpha such that P belongs to U alpha, the cardinality of that is less than infinity. Okay, so that's what it means to be a locally finite covering. And now I'm going to say that a refinement, an open covering V beta with beta in J is a refinement of the covering U alpha with alpha in I. Basically, if every open set here belongs to a unique open set there. Or belongs to exactly one open set, or belongs to at least one. So if basically for every beta, there exists an alpha in I such that V beta is contained in U alpha. It could be contained in more than one, but it's easy to think of two open coverings that don't have this property. Right? So basically, it's basically in a way, this is kind of a smaller, these guys are smaller than those ones. Okay, so they have to be contained in a U alpha. They could be contained in different U alphas, but they have to be contained in at least one. Okay, so that's a refinement. Okay, so let me give a definition, a nice definition, which is of being pair compact. So a topological space is pair compact if any open covering admits a locally finite refinement. That's what it means to be pair compact. And because of our definition of a manifold, we said that a manifold was second countable and Hausdorff. That will imply that it's also paracompact. And it's actually stronger. So I guess maybe let me write down the proposition. Every topological manifold is paracompact. And it's even more than that. Every open covering admits a countable locally finite refinement. So moreover, every open covering admits a countable. This is not necessarily very useful, not always very useful, but sometimes it is. Locally finite refinement. Okay. So how do you prove this? Well, this is actually a fact that applies to more than just topological manifolds. So you can prove this for any locally compact second countable Hausdorff space. So I guess, how do you do this? So the proposition, another proposition that implies that, is that if let X be a locally compact Hausdorff second countable topological space, then X is paracompact. In fact, it has that same property. It's stronger than being paracompact. It admits a countable locally finite refinement. Oh, okay. So how do you prove this? I mean, this is not a course on general topology, so I'm not going to take too long. But let me tell you how you do this anyway. So being locally compact just means that every point has a neighborhood that's precompact, so whose closure is compact. So each point, and let's fix a countable base. So we know it's second countable, so let B be a countable base. So we know that for every point, it has to have a precompact neighborhood. So for each X in X, there exists a neighborhood which is precompact. And basically, since since B is a countable base, you can write this as the union of elements of the base. So you have a subbase of this base, which is whose elements are all precompact. So you can basically write, one way to say this is that you can define this B tilde to be the set of points in B such that V belongs to NX for some X, where NX is a precompact neighborhood of X. Yeah. Pré-compacto significa que o fecho é compacto. So precompact, it just means that the NX bar is compact. Yeah, so being locally compact means that every point has a neighborhood which is precompact. And this is true of topological manifolds, because if every point has a neighborhood which is homeomorphic to an open set in Rn, then, if you're an open set in Rn, then every point has a little neighborhood which is a ball, which is precompact. Okay? So, and if V is an open set that's contained in a precompact set, then it's precompact itself. right? Because the closure is contained in the closure. And a closed set that's contained in a compact set is compact. Okay. So basically, the point is that we can find another base, a subset of this base, which is, of course, countable because it's a subset of a countable set, and all the elements are compact. So this, I'm going to write this like this: V1, V2, etc. Okay, so this is a countable base of precompact sets. Now, what I'm going to do is I'm going to start by choosing an exhaustion of X by compact sets. So I'm going to find so we're going to construct a sequence of compact sets compact subsets such that Ki is contained in the interior, Ki minus 1 is contained in the interior of Ki, and the union of all the Ki's is equal to X. So we're going to construct a sequence like an onion that gets bigger and bigger. So how do you do that? Well, you first take K1 to be, just take the first element, V1 bar. And then now, you know that K1 is compact. So since these VIs, they cover the whole space, they also cover K1. So there's a finite subset of them that covers K1. So then K1 is contained in VI1 union, etc., union VIN. Right? So now you define K2 to be the closure, the union of all these closures. So a finite union of closed sets is closed. A finite union of compact sets is compact. So this is compact, and this is the interior of K2. And then you just apply it by induction. You keep going. Okay? So you can construct the other Ki's inductively. And it's an exercise to show that you have to cover the whole X. Okay. Any questions? No. Okay, now that we constructed them, then now let's show that this property of being pair compact. So now we have to pick an open covering, and we're going to find a refinement which is countable and locally finite. So let W alpha be an open covering. Covering of X. So now for each I in N, we know that Ki minus the interior of Ki minus 1, this is compact. So you can cover that. So we can find we can cover this guy by a finite number of W alphas, which we're going to call W alpha 1I up to W alpha KII. Okay, so like let me just draw a picture. So this is KI, this is KI minus 1. So you find a finite number of these guys that cover what's between KI minus 1, minus the interior of this guy. And then now, the tricky thing is, now we're going to let Vij be W alpha Ji intersection with the interior of Ki plus 1 minus Ki minus 2. So, you have another Ki here. And here you have a Ki minus 2. So what you're trying to do is you're trying to make sure this is locally finite. So you intersect that with what's in here to make sure you're going to have only a finite number around each point. Okay? And that's it. So the point is that these Vij's, this is a countable, locally finite covering, refinement of the original W office. Okay? Is that clear? Oi? Sim. Okay, so first of all, without doing the intersection, you see that you have a countable number of them, right? The problem is if you don't do this intersection, I think up to here you understood. Yeah. So if you don't do the intersection, what happens is you could have infinitely many going through the same point. Like there's no reason, because you just know that they cover Ki minus Ki minus 1. But these could be really open, really long, really big sets. They could all intersect at the origin or whatever. There's no reason for them not to intersect, for them all to intersect at a particular point. But when you intersect it with a bigger set like this, with this guy, then you make sure that in this interval between like I plus 1 and I minus 2, there are only a finite number of them. So since every point has to be in a unique Ki minus 1, and also in a unique Ki plus 1 minus Ki minus 2, then you're basically done. Like you know that this covers everything, and you know that it's a finite refinement. There are only finitely many through each point. Okay? De nada. It's a little tricky, but it's not extremely hard. You just have to think a little bit. Okay. All right. So now, now we need another result. So it's clear that this proposition is a consequence of that, because every topological manifold is locally compact. Okay, so this is proven. So now I actually will do something even a little more subtle, which is about finding refinements that are charts. So I guess I can call it another proposition. So this proposition is the following. So let X be a smooth manifold. I guess this is probably true also for a topological manifold, but I just want to, from now on, just do everything smooth. And fix a covering and let U alpha in I be a covering of X. Then there exists a countable, locally finite refinement of x of, let me call this V beta. Beta and j of the original covering such that basically these V betas are all domains of charts. So such that for each beta, there is a chart phi beta that goes from V beta into Rn, and whose image is a ball. So I'm going to such that the image of this guy is a ball, say, of radius 2. And I want something more. I want that if you just take the ball of radius 1 and you take all the pre-images, that's still a covering. So I want that the pre-image of the ball of radius 1 is still a covering of X. So, if, so say this is your X, that means, I have this guy, this guy, this guy. But then if I take the ball of radius 1, I want to still have a covering. Okay, it's a little hard to draw. But maybe the proof will make this even simpler than just this statement. So let me prove this. And the proof of this is really just a twist of the previous proposition. So if you understood this proposition, this is going to be pretty simple. So proof. So by the proposition above, we can find this the sequence of compact sets, this exhausting sequence. So by the proof of the proposition above, we can find an exhaustion K1 through K2, et cetera to Kn by compact sets. Okay, now, for each point, for each P in Ki, so now we're going to do something that we did here, but it's slightly subtler, just using the charts right away. So for each point in Ki minus the interior of Ki minus 1, we can, so we let UP be an open set. And we can find, and now I'm going to define VIP to be that thing, Ki plus 1 minus Ki minus 2, intersection with UP. And this is still a neighborhood. So this is you pick a certain neighborhood, and this is another neighborhood, a smaller neighborhood of P, admitting a chart such that there exists a chart phi IP. So now I can make this guy sufficiently small so that my chart really has the value on a ball. And I can make the ball of any radius that I want because they're all diffeomorphic. So I can just suppose that these balls, the image here is just contained in, or is equal to the ball of radius 2. Okay, so now I have to be a little subtle because I want that the balls of radius 1 are still covering. So what I'll do is now I look at WIP, which is this phi inverse of the ball of radius 1. But these guys, P. These guys still cover the whole set. These guys still cover the set from Ki minus the intersection of Ki minus 1. Because they're indexed by P, and I'm taking all the P's in there. And now I take a finite subcovering of these guys. So then WIP, this covers Ki minus the interior of Ki minus 1. And it's contained in the interior of I plus 1 minus Ki minus 2. That's just another comment. That's for it to still be locally finite. But then because this guy is compact, I can find a finite subsequence. So there exists a finite subcovering. I can call it WIP1 up to WIPKI of this guy. But this is a subset of these guys. So we have the charts also. So we have a finite number of charts that all are valued in a bigger subset that goes to B2, ball of radius 2. But also the pre-image of the ball of radius 1 still covers the set. So basically let me try to draw the picture again. So in this kind of more specific context, so sort of this is K. So this is Ki, and this is Ki minus 1. So if you have a point P, you have your chart that goes to the ball of radius 2. But you also have a subset of that goes to the ball of radius 1. But since you're letting P range to every point, this, of course, is a covering with this guy. So you take the subcovering that's finite, that's based out of these guys, B1, because you want the one for B1 to still cover the set. Okay, and then you're done. Okay, all right. So that's the end of this. And now we can do now we can actually get to the partitions of unity. Because so let me write the definition of partitions of unity. So I guess, so definition. Let M be a smooth manifold and U alpha be a covering, an open covering. A partition of unity on M subordinate to this covering is a set of functions f beta that go from M to R that's indexed by another thing such that But when you look at the support of these functions, the support is the set of points where the function is non-zero. So the support, so this is the set of points in M such that f of b of x is different from 0, and you take the closure. This is a locally finite refinement of U alpha you have that the value of these functions is always greater than 0. These functions are always greater than 0 for every b. And C, you have that the sum of fb of x over b is equal to 1 for every x in M. And notice that this makes sense. This is not a convergent series. This is always a finite sum. Because this is locally finite. So that means that the value of the function is only different from 0 at a finite number for a finite number of betas. Okay, so this is a partition of unity. So usually we would just write that the sum of fb is equal to 1. Like this. But this is an infinite number of functions. Usually, by construction, it will be countable. Okay? So basically, the theorem now is that given an open covering, a partition of unity always exists. So the theorem will be, given an open covering, U alpha, alpha in I, a partition of unity subordinate to U alpha always exists. Okay. Well, and how do you prove that? Well, we already have almost everything. So the hardest part is what we've already done, is this proposition here. So basically saying that given a covering, we have this countable, locally finite refinement. And what do you do now? You don't even need that it's countable to do this. But what you do now is you have to, first you have to construct a function. So by the proposition above, we have this countable, locally finite refinement with these charts. So we have charts phi beta that go from v beta into the ball of radius 2. So now you use these charts to construct a function whose support is contained in v beta. So now we use these to construct a function fb such that the support of fb is contained in v beta. And we also want that fb is strictly positive in the pre-image of the ball of radius 1. I mean, how do you do that? Like, you just construct a function on Rn that, so if this is your ball of radius 2, I'm going to draw it in one dimension. But if this is your ball of radius 1, and this is your ball of radius 2, you want a function that's 0 here, and that's different from 0, and that's 0 again. It doesn't really matter what it is. If you want, you can choose it to be constant between, on the ball of radius 1, but it doesn't actually matter. All you need is that it's strictly bigger than 0 in here. Okay? So I think you all know how to do that, playing around with exponentials. So something that goes, and then it's 0 here. And you cannot do that analytically, but you can do that C-infinity way. Okay? So once you do that, then you're basically done. So when you do that, this is a locally finite, that this guy here is a locally finite covering. So that means that when you take the sum of f beta, this is actually going to be well defined. So this is locally finite. So for each point, there are only a finite number of f betas which are different from 0. But in fact, there's at least 1. So this is less than infinite, and it's bigger than 0 for every point. So now you just define, I guess I call this f as well. Well, you define phi, you define rho beta to be 1 over the sum times f beta. And this rho beta is going to be the partition of unity. Okay? So that's it. So partitions of unity are very, very useful because it allows you to build certain structures on Rn and then glue them all together for the whole manifold. That's why. But, I know this was kind of a quick overview of partitions of unity, and I went through the proofs of everything kind of quickly, but I think you've seen this before. This is standard material for a manifolds class. If you haven't, can go back and digest this a little more. But do you have any questions? No? Okay. So the last thing I want to talk about today is I want to talk about vector bundles in general. Like we talked about the tangent and the cotangent bundles, but I want to talk about vector bundles. Just a second. These are manifolds with a little bit more structure. So vector bundles. So definition. Let E and M be smooth manifolds and pi be a map from E to M, which is a surjective submersion. Then pi is called a vector bundle if it's a surjective submersion, that means that the preimage is a submanifold for every point. So every point in M is in the image, and it's all the points are regular values because it's a submersion. So that means that I can define EP to be the preimage of P. This is a manifold. But I want to assume, for it to be a vector bundle, that this has the structure of a vector space. So it's diffeomorphic to Rn, but moreover, it has a natural fixed structure of a vector space, such that, with the following property, so such that for every point in M, there exists an open neighborhood and a homeomorphism and a diffeomorphism phi that goes from the preimage of U to U times RK. So it's a vector space, and I'm going to call the dimension of the vector space K. Satisfying. So basically what I want is that the linear structure on the fibers here are given all by the linear structure on RK. Okay, so let me write this down. It means that satisfying two properties. One is that pi composed with phi star, or phi inverse of PV is just P. So that means, when I apply, so if this is pi, and this is the projection onto the second coordinate, projection on the first coordinate, this diagram commutes. So like going here and then going here, projecting is the same as just going here. Okay, I wrote phi inverse for whatever reason, but this is a diffeomorphism anyway. Okay, and the second property is I want the vector space structure on each fiber for each P to be given by the structure from RK. So this means that phi restricted to pi inverse of P. So this goes from pi inverse of P on into P times RK is a vector isomorphism. So this is an isomorphism. Yeah, linear isomorphism. Let me just write. Okay, so this is a vector bundle. Okay? And there are many interesting vector bundles. So maybe one way to start understanding them is by giving some examples. So the first example is the trivial bundle. Oh, and as before, I'm going to assume that the K is constant. I mean, from this property, it has to be locally constant, but I want to assume that it's, it's actually constant. I mean, if the manifold, if the base is connected, then it has to be constant, but I just always want it to be constant. Yeah? No. No. We're not assuming any orientability. So trivial bundle, so you just take a manifold and you take the product with RK with the map given by the projection onto M. This is clearly, it obviously satisfies that property with the standard linear structure on RK. Okay? A more interesting example is the tangent bundle and the cotangent bundle. But let's just write the tangent bundle. So that's, as I said before, it's just the union of all the tangent spaces. And the map is the canonical map that takes something in TPM to P. Okay, so how do you see that? You satisfy that. I basically kind of did that already in the last lecture. But I can kind of rewrite that. So given, how do you prove that that property holds? I mean, it's clear that this is a, actually maybe it's not so clear yet, but it's clear that this is surjective. That this is, submersion is maybe not completely obvious yet, But how do you prove that it's a submersion and it satisfies those properties? Well, so you pick a chart. So this is a chart. And that induces a map phi tilde that goes from the pre-image of u, let me call this pi, into phi of u times Rn. And what is that? That is just, so say you take the sum of vi d dxi at the point P. So for some P in U, and P doesn't have to be the center of U, P is just any point in the chart, you can write a vector, a tangent vector to P like this, because we know this guy is a basis. And now you can take this to phi of P, so the image of P by the chart. This is a subset of Rn. And here, you just, well, let me write AI. And here, you just write the vector AI. So this is almost what I wrote on the previous lecture. Yeah, so it's very easy to see that this is a diffeomorphism. In particular, when you compose that with the projection onto here, you have you can prove that it's a submersion, and it's kind of clear that it satisfies the second property too. Okay? Maybe if you've never seen this before, you have to redo it by your own hands. Like, you can't just watch it being done. You have to kind of try to write it yourself. But there is really nothing. There's nothing else going on here. Okay, so again, you can do also the cotangent bundle if you want. It's exactly the same thing. So these are examples of vector bundles, and we'll see some other ones that are going to come up later. But let me tell you some stuff that you can do with vector bundles. So you can talk about sections. So a section of a vector bundle is a smooth map S from M to E such that pi composed with S is the identity on M. That's what a section is. So this is pi, this is S. And notice that you don't have the identity in the other direction. It's not an inverse, because the map is not usually injective. If k is bigger than 0, then this map can't be injective. So it can't have an inverse, but it's an inverse only in one direction. So that's what a section is. And the notation is, usually we say that, we write it like this: gamma of E. Usually you think of E as being the vector bundle, and the map from M is already, you kind of know what it is. So, I mean, it's really a section of the whole bundle, but you usually think of the vector bundle as being E, and the rest is implicit. So this is the space of smooth sections. On pi. Okay. So now let's talk about some interesting examples. So the first one is the zero section. So every vector bundle has a section called the zero section, which is the following thing. So for each point P in M, when you look at EP, so the fiber above P, so this is the pre-image of P, This is a vector space, so it has a 0. It has a canonical 0. There's a unique element, which is the 0 here. So the 0 section is the function that takes S of P, that takes P to the 0 in EP. This is a canonically defined, this makes sense. It doesn't depend on any choices. And it's an exercise to show that this S is smooth. By definition, it's a section, because you're taking something on the fiber above P. So when you project it by pi, you get back to P. So this property holds. So every vector bundle possesses a section, which is the 0 section. It's often called, 0M is an element of this. And the other thing is you can see the image of any section as, it's not hard to see from here, that the image of a section, that the section is an embedding. So the image of a section is a submanifold of the vector bundle. So remark, I could have said this above, the remark is that the section, every section is an embedding so you can see the image as a submanifold of E. So in particular, every manifold, because the 0 section always exists, every manifold is a sub. Every time you have a vector bundle, you can see the base manifold as a submanifold of the vector bundle. Which is why, in the picture, when people draw vector bundles, they usually say this is M, and this is the vector bundle E, and they write M inside of E. And in this picture, M is seen as the 0 section. But given any other section, if you look at the image of M, that will give you another embedding of M inside of E. Okay? In fact, other sections always exist. As we'll see later in the transversality, you can always perturb sections. Okay? Now I want to talk about sections of the tangent bundle. So, I guess 2. The set of sections of the tangent bundle of a manifold is often called, these are what are called the vector fields on a manifold. So there's a notation for that, which is this letter of M. So these are called vector fields. So what is a vector field? So a vector field is just a map that goes from M to Tm such that S of P is a vector on top of V, of P. That varies smoothly. So this is what a vector field is. So it's a section of the tangent bundle. Vector fields always exist because you can always take the 0 vector field, the 0 section, but it's not easy, and sometimes it's not true that you can always find a non-zero vector field. So non-zero sections don't necessarily exist. So a very beautiful theorem is called the Harry-Ball theorem, and we're going to prove it in this course. It says that if V is a vector field on a sphere and n is even, then V has a 0. So that means, there exists a point such that V of P is 0. And And that's called the Hairy-Boll theorem because you can think of your sphere, and you can think of, you put some hair in it, and you try to comb the sphere. And then the point is, you cannot comb the sphere without having a place where you have a zero of your point. Ou em português, a redemoinho. So in fact, it's usually you have two. We'll talk about this in a lot of detail. Generically, you have two. It's possible to just have one, but if you perturb that, it'll be two zeros. So this is going to be part of the transversality theorem, or intersection. Okay, so this is vector fields. Now let's talk about sections of the cotangent bundle. So more examples. So sections of the cotangent bundle are called differential one-forms. So they have this name. So they're called differential one-forms. And I mean, we already know what they are because they're sections of a vector bundle. So at each point of the manifold, you choose a covector. And it's a nice, as I told you earlier, if you have a function, a smooth function, that gives rise to the f, a differential, which is a section of the cotangent bundle. So this is a one-form. Not every one-form is of this form, but this is a way to construct a lot of one-forms. Okay? And it's defined like this. One way to see is if you can think of it as defined like this. If you take a vector field and a function, you define df of v to be f applied to v, to v applied to f. Okay, it's very canonical. Okay, now a more interesting example. So let's talk about metrics, Riemannian metrics. So what's a Riemannian metric? So if you have a vector bundle, you can do operations on the vector bundles, like the same operations that you can do with vector spaces, you can do with vector bundles. So given a vector space, a vector bundle, you can look at the dual vector bundle. So the dual vector bundle is just you take, for each vector space, for each fiber, you take the dual vector space, and you glue them together in a consistent way. So you can do this operation. I'm not going to prove, but it's pretty canonical. Okay? And now you can do what's called the symmetric product. So, you know, you can do, given a vector space, you can look at the symmetric product of this space, which is basically you take the tensor of two vector spaces and you quotient by yeah, well, let me write the definition here. I wrote this down. So what is the symmetric product of E star of P? This is the set of bilinear symmetric two forms on EP star. Okay, so it's basically the set of functions that, on EP. So it's a set of bilinear functions such that f is bilinear and symmetric. Yeah, so it's basically the tensor product quotiented out by switching the order. Okay, so it's a set of things So you can do that for every tangent space, for every fiber. So now you can construct a bundle, which is called the symmetric bundle of E star. So this is a bundle over M. And a metric on E is a section of this bundle which is positive definite. I mean, I'm using the language of bundles a little bit here, but another way is to just say, what is a metric? Well, a metric is just a function that for each p will give you a bilinear symmetric and positive definite form, a function. And such that it varies smoothly with p. That's why, I kind of made this definition and said it was a section. Because that is what it means to vary smoothly with respect to p. Okay? And then now we can prove that a metric always exists using our partitions of unity. So proposition, any vector bundle admits a metric. Well, how do you prove that? Well, so take your vector bundle, and then now what you can do is, so for each point you can find, so for each p, I could really leave this as an exercise, but anyway, let me do it. So for each point, we can find a metric on, so for each point, first you get an open set. You choose a neighborhood of p such that pi inverse of up is diffeomorphic to up times rk. And then now you find that you take the standard inner product on rk. And now you take a finite subcovering. So you take the standard inner product here, and then you take a finite, a locally finite refinement, and you get a partition of unity like before. And a partition of unity so basically so you have your locally finite refinement and a partition of unity, which I'm just going to call phi j and j, and then you have the pj which corresponds to that. So you have this metric gpj. And I would just take the sum of psi j, gpj, and that's going to be a metric this is a metric. on E. And because it's a covering, it'll be positive somewhere, so it'll be still positive definite, it'll be symmetric, and this is a finite sum at each point, so it's well defined. Okay, so this was really fast, but if you have never seen it, maybe you can try to do it by yourself as an exercise too. Okay? In particular, every manifold admits what's called a Riemannian metric. So a Riemannian metric is a metric on the tangent bundle. A Riemannian metric is a metric on the tangent bundle. So as a consequence of this, every manifold admits a Riemannian metric. So we might use this, we're going to use this fact sometimes. Not a lot. This is not a Riemannian geometry course, but sometimes you do use that. So if you now if M is a manifold and G is a Riemannian metric, now to a function we can associate a vector field. That's called the gradient vector field. It's not as canonical as the differential, which is a one form, but it's possible to define if in the presence of Riemannian metric. So if you fix a function, a smooth function, now you can define the gradient of f to be the following thing: the unique vector field that satisfies that g of the gradient of f dot is equal to df. So, in other words, the Riemannian metric will give you what's called G sharp, which is a map from the tangent space to the cotangent space that takes v to g of v dot. And when you take the inverse of this map, apply to the differential, you get a vector, and that varies smoothly, and that's called the gradient. So given a function, you do have a gradient vector field, but it's really not as canonical as the differential, because it depends on the Riemannian metric. Okay? All right. Let's stop for a breath. Any questions? Well, there's one more thing I want to say about manifolds before we finish today's lecture, which is about integration of vector fields. Which might be useful. So, integration of vector fields. So I guess a theorem. So if V is a vector field on a manifold and P is a point in M, then there exists a unique curve gamma from minus epsilon to epsilon into M such that the derivative of the curve is the vector field and gamma of 0 is P. So, given a vector field, if you pick a point to be 0, there's a unique curve that goes to this point that's tangent to the vector field. Of course, you might have to make epsilon sufficiently small. So for epsilon sufficiently small. Okay, this is the kind of fundamental theorem of ODE. It's called the Picard-Lindelöf theorem. I'm, of course, not going to prove this right now, but you can, it's a beautiful, very beautiful result. You probably have all seen this before using the contraction theorem. And then the other result, which is also very classical, very important, is that if you move P, then in a smooth way, then this curve, the solution to the ODE also moves smoothly. So this basically means that there is something called the flow, and the flow is a smooth map. So the solution to this ODE at time t is called the flow. So you can define this phi t of P, which is basically the gamma at time t. So the solution of the ODE at time t. And this is defined for t sufficiently small. So a proposition, which has to do with varying the solution of ODE in a smooth way, is that in a small neighborhood, of P, the small neighborhood of P, phi t, is defined for sufficiently small t, and phi t is smooth. Moreover, we can write that phi of t plus s is equal to phi t composed with phi s whenever it's defined. And the other thing that you can see is if the vector field has compact support, so if it's 0 outside of a compact set, then this flow is always defined for all time, for all P. I mean, it's always defined for all P for sufficiently small time. But, so I guess the remark is if, and this is just a consequence of being compact, of the support being compact. So if V is a vector field, if it has compact support, then phi t from M to M is defined for all t, which implies in particular that it's a diffeomorphism, because you can apply phi t and then you can compose with phi minus t. And this is the same as phi minus t composed with phi t, which is the identity on M. Okay, in particular, moreover, okay, so we have this, these things are called flows, and they're very useful, especially if the vector field has compact support. Okay, so we're going to use that fair amount. And I think I'm going to stop now for the lecture. So yeah, we're going to continue on Monday. But just before I stop, a few administrative things. I'm going to post the problem set tomorrow by the end of the day. And then you'll have a monitoria with a TA. So meeting with the TA on Google Meet at some point later this week. He'll let you know on the Google Classroom. Okay? So if you have any questions about today's class, you can send me an email if you're on YouTube. And maybe next week we can maybe find some time to talk on Google Meet if there are some more questions. But for now, you can also ask the TA, the monitor. Okay, so see you next week.